let's now take a look at an example. So in this example, we want to create a Routh table for the system that's shown below. So as always, I would encourage you all to pause the video and try to set up or work through the problem by yourself before coming back to see the solution here. So it might be tempting to look at this forward transfer function and say, all right, we have a pole at -2, a pole at -3, and a pole at -5. All of them are in the left half plane, so our system must be stable. But that would be incorrect. So remember, the very first thing that we need to do is we need to find the equivalent transfer function. So we need to find our equivalent transfer function. And so in this case, just like we saw in a previous video, we just have a simple feedback form. So we have unity feedback and it's being subtracted here at this summing junction with our input. So what we can do then is we can say our GEQ is equal to G divided by 1 plus G, and then our H is just a 1. So to make this a little simpler, because this is something we see often, of course our G is going to be some numerator and some denominator. So in this case, the numerator is 1000. The denominator is the product of those three polynomials. So we have that as our G. So now we're going to also have this term over here. So we're going to have our numerator of our G, our denominator of our G, and that's just being multiplied by 1. So if we want to add 1 to that, of course, what we typically are going to do is find a common denominator. And so if we do that with 1, we're going to have denominator divided by denominator. So of course, this is just a special value of 1. So if we do that, what we're going to see is in the numerator of our overall transfer function, we'll have num over den, and then we combine that denominator to get denominator plus numerator divided by our denominator. So we found a common denominator of den down in the denominator. Lots of denominators and numerators floating around. Hopefully that wasn't too difficult to follow. But now we can cross out these two, and what we're left with is just numerator over our denominator plus our numerator. And so that's an easy way to deal with these unity feedback functions. So that only applies if we have a unity feedback. We don't have any gain in our feedback path. So if we do that for this case, we can see that we're going to have an s cubed plus 10s squared plus 31s. We would have a plus 30, and then we're going to add the numerator, which was 1000. So our overall constant value here becomes 1030, and then we just have the numerator up here of 1000. And so this is going to be our overall equivalent transfer function. We have our output C of S on the right and our input R of S over here on the left. Okay, so now that we have made our equivalent transfer function, we're ready to make our Routh table. So let me go ahead and drop this down a little bit. So remember, the first step is we're going to want to label our rows with powers of S starting at this highest order, which is S cubed, all the way down to S to the 0. So just to sort of be consistent with what we did last time, for this first example at least, I'm going to do these initial values that we're getting directly from our transfer function in blue. So we can say we have S cubed, S squared, S to the first power, and S to the 0. And so of course what we can see is this is going to be a smaller Routh table than the previous video, and if we have higher orders, it's going to be a larger Routh table. So the next step is we're going to populate the first row, so our S cubed row. And we're going to do that by looking at our S cubed coefficient. We're going to skip a coefficient to go to our S coefficient, and then we skip the next one and we don't have anything left. So it's just going to be those two coefficients. So we're going to have a 1 and a 31. And if we want, we can go ahead, remember, we can have zeros as far out as we want there. So let's just go ahead and put 1, 0 right now for the time being. Again, we don't need to put that, but let's just put that because let's say you're working through this and you weren't sure if you need to have a 0 or not. So what we do next then is we come back up here, and for our second row, our S squared row, we're going to go to the coefficients we skipped. So we skipped over this 10 for our S squared, and we skipped over this 1030. So we're going to come back down here, and we're going to say we have 10 and 1030. And again, maybe you're not as familiar with when we can stop, when we need zeros, when we don't. So we can just go ahead and put zeros there if we want. but we don't necessarily need to have that, as we're going to see in a little bit. Okay, so that would be all of the information that we get directly from our equivalent transfer function. Again, we can put this bar sort of above and below if we want to have the same style as the textbook, but we don't need that either. So one other note I want to mention is that we can multiply rows by a positive constant to simplify things if needed. So we can multiply entire rows by a constant to simplify. So one sort of constraint here that I've left off is that it does need to be a positive constant. So this constant that we're multiplying does have to be greater than 0. And so the reason I mention that here is we can actually make things a little bit easier if we wanted to with this second row. So instead of second row, let me say my s squared row. If we wanted to, we could multiply by 1/10. So if we multiply that row by 1/10, of course what we're going to have is the 10 is going to become a 1, and our 1030 is going to become 103. And so again, that just makes it so we're dealing with, you know, a little bit smaller numbers. We don't have as many of these zeros floating around, but we don't have to do that. And to be consistent with the notes that I have posted on Canvas, I'm going to leave our S2 row as we see here, or our S squared row, but you could go through and you could work it with 1 and 103 and confirm that we get the same thing. Okay, so our blue values are what we populated from our general transfer function. So now we need to figure out the remaining entries. So we could call this B1. Again, let's say we don't necessarily know when to stop, so we could just, if we wanted to be safe, we're not really comfortable with this yet, we could define B2 and B3 if we needed. And down here in the next row, we have C1, C2, and C3. And so what we could note is I could go ahead and say that most of these are going to be 0, and we'll come back and we'll say why that is in a little bit, but you don't necessarily need to have those once you're more comfortable with this. So the next step then is going to be to calculate these other black coefficient values here using that general equation we talked about in the previous video. So let's start by calculating our B1 value. So remember, we're going to have the negative of some determinant of a 2 by 2 matrix divided by some constant value. So for our B1, we have this is our first column, this is our second column. So we have 1 and 10, and we have 31 and 1030. And so you can see that if we had reduced that 10 and 130, or sorry, 10 and 1030 to a 1 and 103, of course we have a reduction by a factor of 10 when we take this product, and a reduction by a factor of 10 when we take this product. So the two reductions sort of cancel out. And then we're dividing that by 10. So if you plug in and calculate that, you should get a value of negative 72. So now for our B2, we're going to be using the same, our same two entries for our first column, so that doesn't change as long as we're in this B row. But now instead of 31 and 0, we're using these two zeros here. And so as we saw before, we're going to have 1 times 0 minus 10 times 0, which is just going to be 0. So we can say that our B2 is going to be 0. And same argument for our B3. So again, we could think about there being zeros over here. So our B3 would be this 1 and 10 for our first column, and then our zeros again here. So our B3 is also going to be 0. All right, so moving on to our next row, we have our C1, which is also going to be negative determinant of a 2 by 2 matrix divided by something. So now that we're looking at C1, we're going to have our first column is going to be 10 and B1, and our second column is going to be 1030 and B2. And that's going to be divided by our B1 here. So we come down here and we can say we have 10, and we found that our B1 was negative 72. We have our, let's see, we had our 1030 here, and then we found our B2. We said that turned out to be just a 0 value, and then we divide by the negative 72. What we can see is, of course, this is going to be 0, so we're going to have negative 72 times 1030. We have another negative sign, so 3 negative signs means ultimately or sorry, we have 4 because we're subtracting this. So those are all going to cancel out, and we're ultimately just going to get 1030 because the 72 here is going to cancel out with the 72 here. But again, you can step through that full calculation if that's not immediately evident just looking at it. So the next item then is our C2. So for C2, we're staying in this first column for the first column of our matrix, but now we're coming over here. So we're moving right 1 column and up 2 rows. So we said B3 was 0. So again, we're going to have 10 times 0 minus B1 times 0. So we have 0 in the numerator. So our C2 is going to be 0. And we can see the same argument can be made for our C3. So both of those are going to be 0. Okay, so now we have a completed Routh table. So let me just come back up here and erase these terms here and just repopulate it with what we found. So that's going to be easier than redrawing the whole thing, I think. So we have our Routh table is going to be negative 72, 0, 0, and 1030, 0, 0. Okay, so this is our Routh table. So now what we want to talk about is how do we interpret this Routh table. So interpreting our Routh table, so it turns out it's pretty straightforward, and we're going to talk about sort of some exceptions to this case or some how we deal with sort of odd cases in some later examples. But basically what it is all we're looking at is number of sign changes in the first column. So number of sign changes in the first column is going to be equal to the number of poles in the right half plane. So number of sign changes in our first column is equal to number of poles in the right half plane. And so that's very important. So we'll highlight that. So that's important to know, of course, how to interpret this Routh table. So for this example, we see we have 2 sign changes. So we have 2 sign changes above, which means we have 2 poles in our right half plane. And so where are the 2 sign changes? We can see we have 1 sign change. So we're looking at our first column here. So we have 1 sign change as we go from 10 to negative 72. So that's going from positive to negative. And then a second sign change as we go from negative 72 to positive 1030. So this is our first sign change. This is our second sign change. And so because of that, we say we have 2 poles in the right half plane. And because this was a third order system, so coming back up here, the highest order is 3, so we know this is a third order system, which means we're going to have 3 poles. So third, yeah, it's not behaving today. So third order system means we have 3 poles in total, and we've identified the general location of 2 of them. So that just means it's told us that we have 2 in the right half plane. So because we have 2 poles in right half plane, we know we have 3 in total. That means we have 1 remaining pole, which is in our left half plane. So 1 pole in left half plane, 2 poles in the right half plane. And so ultimately what that means then, because we have any amount of poles in our right half plane, that our system is going to be unstable. And so a couple things to point out. Again, notice that with this function, neither of our quick checks for instability flagged this as being unstable. So again, that's just telling us that if a system is unstable, it's not necessarily saying the system is stable if it passes those 2 quick checks. And then another sort of more general question that you might be saying is, well, we've looked at how to do some of this stuff in MATLAB or with a calculator, so I could find my equivalent transfer function pretty easily. And then from here, I could just use a function to figure out what my 3 poles are for this equation here. And so that's 100% true. We could know the exact locations as opposed to the general locations. However, we're going to see in the next example that if we have some variable some variable gain k anywhere in our system, the power of our Routh table is we're going to easily be able to determine the range of that gain, which is going to give us system stability. And so of course that's not something that we could easily do by using a roots function or something similar in MATLAB or a calculator.